I forgot anymore. My God, I need to die.
Alright, so... Do I have to calculate this using a circular curvature?
Is this recording now?
No. Shoot.
Okay, cool. I think this is working.
Well, it says relative to the Earth, and I'm thinking, to what? The Earth is a flat...
Like, why would it put relative to the Earth?
Consider Earth to be flat.
I'm live streaming the class because I'm.
Okay, consider Earth to be flat.
There you go.
Can it still see the board?
Still different.
Nope, people are too tall. That's okay. We can just listen. No, we can't. This is a horrible idea.
Yeah. Okay.
Yeah. No, this is good.
Okay, that's cool. Last time, Tuesday, if you hadn't noticed, it was kind of crazy. And that schedule made me go a little faster than I like to go. So if things were confusing, I apologize. I would have liked 10 more minutes to spend on that topic, but we did not have it. So we'll try and maybe clear things up today. But anyway, the fact is, you don't learn from my lectures, even though you always believe you do. You learn from the homework. So let's take a look at that homework.
Sorry.
Middle of the computers.
We'll give you the answers first, and then we'll go over the homework. I like to do 10-question homeworks with a challenge problem. The reason is people ask for more homework. Okay, so I get it. The challenge problems are hard. We're not going to cover them in class because they take too much time. Okay, they're designed to be very difficult, as much as I can with what we have. Sometimes they're only kind of difficult, sometimes they're extremely difficult, it depends. So the point is, I'll give you the answer, but I'm not going to cover that question in class. However, any of the other 10 problems I consider foundational, important problems, and I watch your questions if you have them. Okay, so I'll give you all the answers, and you give me questions, we'll talk about them. Okay, number 1 is 120 miles per hour. Number 2 is 90 miles an hour. Number 3 is 0. Number 4 is 14 meters. Number 5 is, sorry, I don't have these, because these are computer generated, I only have them in decimal form, sorry. You should be able to figure out if you're right or not, just by approximation, or with a calculator. So number 5 is 16.3 meters. And number 6 is 116.6 meters per second. Number 7 is B. Number 8, I did tell you the bomb is the origin, right? So, okay, we'll all agree on this. So the bomb is 0, 0, 0, 0. And the light would be 1 second, 6 meters, 0, 0. You should put the units on there. Just because it's a coordinate system doesn't mean it doesn't have units. Number 9 is negative 2 meters per second. Negative 2 meters per second. Number 10, the bomb would still be 0, 0, 0, 0, but the light would be 1 second, 8 meters, 0, 0. And the answer to the challenge is 10 meters per second. Okay, questions on 1 through 10? I'd be happy to talk about anything that's confusing. Anyone have anything I can talk about? Go ahead.
Just 5 really quick.
Say it again?
5.
5, okay. 5 is Rosencrantz Guildenstern, right? Yes, so this is very, very important. For understanding what's going on. In Rosencrantz's reference frame, with all of this going on, everything is fine. In Rosencrantz, the one on the what vehicle is this? It's a crystal ball. The crystal ball. Crystals you can see through. So Rosencrantz on the crystal bus, everything was up and down, very simple. Guildenstern is over here, watching the bus move. So Rosencrantz sees the bus stationary, Guildenstern sees the bus moving. Therefore, what trajectory does he see the ball moving? Good, he sees it going diagonal and back down like that, right? Do I do round trip or one way? What? Round trip, okay, thank you. Okay, good. So that means this ball compared to this ball, and it's the same ball, but in Guildenstern's reference frame, that ball is traveling. Compared to this one, the ball has to be traveling, okay, faster and also farther, right? Number 5 is about distance, so it's going to be a longer distance, right? Because look at it, right? The height is the same. What's the height? 7 meters. Okay. But it's also traveling this way. So obviously it has to be going a greater distance. Well, the distance it's going is greater by this amount. This amount is v times t in general, right? Let's say it's how far the train travels in that time. And that distance is always v times t. V being the velocity of the train, which is, what's it? 6 meters per second? Okay, good. So that's to say, so v is 6 meters per second, and t I actually don't know yet. Okay, but I do have it from doing Rosencrantz. What's the time it takes the ball to reach from the bottom to the top? 7.07 seconds? Okay, I'm just trusting you on that. Okay, so we already found that it takes 0.07 seconds for it to get down from the bottom to the top. Now here, of course, you're like, well, obviously it's going to take the same amount of time, right? So therefore, t is still 0.07 seconds, right? Now, why are you belaboring this point? You'll see. But I just emphasized that t is the same as this t, right? So really, this thing is 6 times t, so it's 6 times 0.07. Right? 6d? Yes. Oh, I didn't hear that. Okay, 6d. So it's 6d times 0.07, which is still fine. Which is what? 4.2, good. That one I do expect you to be able to do without a calculator, for the record. So I had a question on this. The homework, often you'll need a calculator, especially to get a numerical answer at the end. And sometimes the numbers are a bit too bad, and you'll need to use a calculator to break through them. That is okay. However, the tests, you guys, because the homework is computer generated, the tests are hand done, and so the numbers will be nice enough that you can use. Okay. So that's what I meant when I said I don't want calculators. That's for the tests. The homework you should try and do as much as you can without it. If you hit something like this, you should not be reaching for your calculator, right? But if you want to reduce the square root of 18,522, then go ahead and use your calculator. All right. So 4.2 watts. Meters, good, because this is the distance that it travels. So what we have here is a triangle where this is 4.2 meters and this is 7 meters, and so finding the hypotenuse of this triangle is now easy, right? Use the Pythagorean theorem, and you have to multiply by 2 because it goes back down the other side, but it's going to be the same on the other side. Okay, so you can do that easily enough. This one you want to use a calculator, right? Okay, and so that's how you figure out the distance. Once you have 5, 6 is easy because you have the distance and the time. It's easy to find the velocity. Okay. All right. Are there other questions on the homework? Yes.
The slide 9.
Good. Very, very important. I didn't have enough time last night. This is really, really important. It is actually the only hard part about relativity. I don't know if that's true. That's probably not really true. But it's probably the hardest part is the minus signs and the plus signs and getting them right. Because if you change the sign, you get the opposite answer, right? And so it's very, very important. Whenever you're doing that, so I'm going to view this thing, even though it's pretty easy to do those 8, 9, and 10, like just with like a little bit of common sense, right? It's very straightforward. But I want to do it in mathematical detail because this is how we're going to have to do things later. There's one reference frame that contains an event coordinate that we know. That is, in this case, 1 second 6 meters, if I recall, right? That's what we found in number 8. Okay, so there's a known coordinate, a reference frame with a known value, and another reference frame with an unknown coordinate, right? This is the unknown t prime, x prime, y prime, z prime. Right? Yes?
For the first one's with the reference frame of the plus, right?
Right, well, I just want to make sure there's always one you know and one you want to know. And so what is the one we know? What reference frame is that?
It's the one with the train.
The train's reference frame. Okay, so that tells you, this is a lousy marker. That tells you this is the train's reference frame. Okay, and this is which reference frame? The Earth's reference frame. Okay. Now, we always have v defined in positive x direction. Right? And v is always the velocity of the reference frame that you want compared to the reference frame that you already know. Okay? It is important to do this. This is like all the difficulty, or much of the difficulty in relativity comes down to this, getting the minus sign right. So you always have one of these reference frames is the one that you already know. Wow, look at that one too. And one of them is one that you want. Does that make sense? There's one where you know the core vector. You just look at the coordinates and you see how they work. And then you want to know what is it in another one. So that's usually the question it's asking, right? So number 10 says, what is it in the Earth's reference frame? You've already figured it out in the strange reference frame. So that means, so V is the velocity of the one of the frame you want relative to the one you know. Okay, it's always the velocity of the frame you want, the frame you are going into, the frame you're transforming into. Okay, the one that we want to know about. Okay, in this case, which is the frame we want? Which frame is the one that we want to know about? The Earth's, right? The Earth is the one that we're trying to find out. So that means it's the velocity. Oh, that's nice. Ooh. Velocity of the Earth relative to what's the one we know? The train. Okay? So V must be the velocity of the Earth relative to the train. Now, did I give you the velocity of the Earth relative to the train? Technically, no. What did I give you? I gave you the velocity of the train relative to the Earth. I told you the train was moving in the positive direction relative to 2 meters per second relative to the Earth. Okay? That means that what's the velocity of the Earth relative to the train? Same speed, but going the other direction. Okay? So it's just a matter of getting the sign right. From this, we say, therefore, V equals negative 2 meters per second. And if you plug that into your Lorentz transformations, you get an answer that makes sense. Sir?
Is this like...
That meant Galilean transformation. Yes.
With like the x minus vt, you have like 6 minus the negative 2 times 1.
Good, right. When you're doing the transformation, let's just do that. We had this rule, right? This is the Galilean transformation. So you take x prime is going to be the original x coordinate, that's 6, minus v, that's negative 2, times t, that's 1. Right, so it's plugged in, and that gives you 6 plus 2, which is 8.
So in the first example, we're talking about the train, the light on the train, in relation to the explosion, the origin of the train.
In this picture here,
Yes.
the origin is,
Like over time, origins.
okay, origin means just the spatial origin, right?
Yeah, because you talk about the origin being model.
Okay, the coordinate system, like the spatial coordinate system, this one is the one that is fixed in the train, right? And this is the one that is fixed on the Earth. So they both move relative to each other, right? So from this point of view, the Earth is actually moving this way, right? And from the Earth's point of view, the train is moving this way. So it's a matter of getting the sign right. Okay, it's very important. It's worth considering. We will do this thing with velocity a lot, and it will get the other stuff will get harder. So it's important to make sure this part will stay the same, but we have to make sure we understand it. Okay, it's always which reference frame do I want to know? That's the velocity I need to know, right? Which direction is it moving then? Is a crucial point. Good. Any other questions? Excellent. As I said, I'm not going to collect this. So I'm not going to collect this. All right, great. Well, what should I do first? Physics or syllabus?
Syllabus.
Syllabus? All right. First person to respond to syllabus. Syllabus is on the Moodle, but I can put it over here so you don't have to, because you don't like to have a lot of space, I've noticed. So, unfortunately, because of the construction in the B-wing, we're already at a premium for space, and so I cannot move us to a larger room because they're already cramming like mad and organic and MCD into other rooms around campus, so there's really no room left. Okay, so let's go over this. So the syllabus is on Moodle. here's syllabus. Can you guys see okay? That's me. Dr. Don, that's me. Let me zoom in a little bit. And this is my email. It's the best way to reach me. I guess you can call that's my office phone. If you call it, I'll answer. But email is the best way to reach me. I respond to email. I check my email pretty frequently, at the very least once a day, but usually quite a bit more than that. So I'll respond to email. It's the best way to contact me. You, by the way, if you don't check your email at least once a day, you need to. Email is currently our mode of official communication, right? If an employer is trying to contact you, they're not going to Facebook you, right? You have to check your email. You're like approaching like officialness, you know. Blah blah blah. Okay, these dates are important. I'm pretty sure they are right. I'm pretty sure they're not going to change. I was looking over the schedule. They are Wednesday, October 5th, and Wednesday, December 7th. Those are both Wednesdays. They're I days. And that night, 7:30 p.m., we are going to have our tests. We have our tests at night. There's two reasons for that. One is that we have two sections, and some of you are dirty liars and cheaters. So that because of that, you have to make adjustments. And then also because that allows you to take more time for the test. You're not limited to 55 minutes, and you'll thank me for that when you take the test. So anyway, we do night tests in this class. There are just two of them on those dates. I expect you to free of those dates. Okay? If there's a conflict that you know of in advance, something very important which happens, that's fine. Please tell me, and we'll work out an alternative. Please tell me in advance. The rules say a week in advance, excepting if you get sick or something like that. Right? Obviously, you don't tell me that a week in advance. I'll be very suspicious. So, and then the other one, Monday, November 28th. That is the Monday after Thanksgiving break. Because of SIR scheduling, we don't have a good time to leave school to go somewhere. So I picked that Monday as hopefully the time the teachers have the least big stuff due because it's right after Thanksgiving, or our parents do, the least big stuff going on because it's right after Thanksgiving. So I'm hoping they don't have big presentations or stuff going on then. I'm trying to help to make this easier for my colleagues, but this is when we go to Fermilab. And we're going to Fermilab partly to look at it and have fun, and partly to give our final presentation. I'll talk about that in a moment. So these 3 dates I expect you to clear up. I expect you to put them down in your calendars, and when people say, can we do something then, you'd be like, no, we cannot, right? And this one, just to why, I mean, you're not going to hear stuff from your other speakers for a while, but like if something comes up, please let me know as soon as possible. And this is one that really can't be made up, you know? So we really have to look hard at alternatives, but in general, like, this is a class expectation and an important part of the class. Okay? Yes?
Number 28.
Oh, that's really interesting. 27. I will go change that. Figure out what I'll do right now. Thank you.
Oh, it's
I will go fix that, of course. It's the 27th, the Monday. The Monday is the right part. Okay. I actually have to confirm that with Fermilab, but they've always been helpful far enough in advance. It should be fine. Okay? Please reserve those dates. If you have a problem with them, see me as early as possible. Yes, sir?
October 5th is a Thursday.
Wow. Wait a minute. This is the wrong syllabus.
Darn.
Hang on a second. These days look better? Okay, I dragged up the wrong syllabus on Google Foods.
Is everything else the same?
Sorry about that. Thank you for catching that. All right, we will now continue. I must put up the wrong syllabus. I will fix that. So those dates. One thing I was saying, the one that actually, they're both very close, but I think of the December one we start with it. Okay. Absence and parties. I am strict on absence and parties in general. Oops, I may need to send it in, but everyone was here today. And then there's stuff in here. You can take a look at it. It's not a big deal. I follow this policy. I'm pretty strict on it. I follow the clock, which is on like my computer, for example. students. When you're taking tests, I expect answers that reduce fractions and reduce radicals. Okay? Reduce these. So like if you put 15 over 30, you will not get full credit. If you put the square root of 20, you will not get full credit because that's 2 root 5, right? So I expect you to be able to do things like that. Some people seem to be really surprised by this news that you can possibly expect that without a rocket. So I just want to make sure it's out there. Computers, regular computers, we don't use them every day, we use them fairly often. So you should need them anyway, right? So, and bring your charger with you. Your battery's going to die over time. If it hasn't happened to you yet, it will this year. You notice the seniors always plug in stuff right away. Okay, so here are the assessments. I give homework every day. I don't collect it. This is on purpose for a variety of reasons. One is to make things easier to me, but I also think it makes things easier for you in that, like, right now should be okay. You should be able to get homework done right now, it seems like. But, you know, some days you'll have, 2 tests and a midterm the next day. Then, like, you're like, wow, I really don't want to do my ModPhys homework on top of that. Okay, don't, right? But pick it up later when your schedule eases up a little bit, right? Getting a day off from homework is not going to kill you, right? You'll just have to make up for it a little bit later. Getting 4 days off from homework is still not going to kill you, but it's going to be more problematic over time, right? You don't want to get much off of it because it's going to be very hard to catch up because I do assign it every day. But the point is, part of the reason not collecting it is to give you a little bit of flexibility, try and take off a little pressure, but I want to not take off too much pressure. You need to do the homework. If you don't do the homework, you're going to be in big trouble. So if you have trouble with the homework, you are welcome to email me, and I'll do the best. If it's during the day, you can find me, right? If not, you can email me, or you can, but you have 30 people in this class, so you are welcomed, you should, and the other class as well, right? So, plus people who've taken it before. So you have a lot of people to ask, and you should ask them, right? By all means, find formal groups that work on homework together. It's a great thing to do. It's a great thing to do in college as well. Like, homework groups are really important. You learn a lot that way. So if you're having any trouble, find some people to work with. It's the best way to do homework, in my opinion. Okay, quizzes. They come out about every 2 weeks-ish. And they're in class, they're level, sort of like the SI physics ones, level 1, level 2, level 3. I actually like that a lot, so I level them. But they're not all or nothing like the SI ones are. I'll give first credit. So so you have that. So that's how the quizzes work. They come from time to time. Then exams are those 2 ones. They're at night. They're big. They're difficult. Okay. If the quizzes are level 1, level 2, level 3, the exams are from SI physics, and the exams are more like integrated. That's right. So they're fairly difficult. Then there's a project. We will talk more about it in general. The project is going to be in groups, a lot of them in this class. You're going to have groups, and you're going to be designing a particle detector and accelerator complex. And you are going to be designing it in quite a bit of detail in your group, and you're going to be competing with each other to see who is going to be the design that we actually choose. And when we go to the lab, you are going to present it to a physicist who is going to evaluate your design.
Oh boy.
Yeah.
How many people are in the group?
That's an interesting question. I haven't figured it out yet. I can't figure out whether it's a reasonable number or a giant number. I'm thinking about it.
Flashbacks to 7th grade science.
The winners of various things in there get additional points. You will. It's not like an all or nothing thing.
Automatic aid.
But there are points associated with it. Yes. I will give you more information. We're not going to start on this for quite some time. Not until basically the end of the relativity unit, because you need some basic relativity before you can talk about anything else. Okay, so we'll get into that. Grade breakdown is 40% quizzes, 20% exams, 40% project. Okay? Early on, you're only going to have quiz grades in, so they'll dominate both, because we're not going to have project grades still for a while, but they will start floating in later on. We'll have a lot of project stuff later on. Okay? Grades, blah, blah, blah. Okay? Oh, is there a final? Yeah. Tucker and I both really like doing finals, actually. We discovered it's great. So there's definitely a final. The final will be put in with the other categories. I've not decided exactly how to do it yet, because I haven't decided exactly what your final's going to be this year. I like to surprise you guys.
What is that?
Last year, for example, it was half project, half exam. Was how I did it. But this year, I'm not sure what I think about that. I'm still kind of decide. I will let you know about
The final was a program that was so traumatizing that the other students wouldn't talk about it. They even added resources that including internet access in an hour and a half to do it, and a bunch of people still got C's.
I don't do pop quizzes. I will tell you well
I mean, you do contests.
Oh, what an interesting question. I do have, so there's two big units, relativity quantum mechanics, that make up this class. It usually have 3, I think, subunits. Each one has a quiz on it. And at the end, I will give you an option shortly before the test. Usually the Monday before the test, which is on Wednesday, right? So the Monday before, I give what I call a redemption quiz, which is your chance to redeem yourself from your sins on your previous quiz. You can't get all your points back like an SI, but you can get some of them back, and you're welcome. Okay, that's a good question. Anything else about the class structure and stuff? Okay, in a given class, there's just homework. There will be, we'll come in, we'll talk about physics, we'll give you more homework, and it'll work like that until we hit project time. Projects are very different. They'll be, working on groups and stuff. And I will give you some class time to work, but you'll also probably need some outside. But you will definitely have class time to work on things. You'll need to ask yourself. Okay, so ready to talk physics? Yeah. All right, let's do it. So, the story of modern physics is really the story of the most difficult, complicated, what's the word, substance, thing. Okay, the most difficult, complicated thing to deal with in the regular difficult, complicated stuff in the regular world is to understand. Math is not stuff. In like the regular world that everyone interacts with, so the answer is not like books. You know what I mean? Like regular things. What's the close to?
Light.
Good. Light. Light is different from everything else. It's weird. And the more we study it, the more we found
we don't
find that it's weird like everything else. Eventually we figured out there's an answer to this. We actually have a pretty good grasp on what light is now. But it took a long time to reach there because it doesn't obey anything else. Hey, Newton's laws of motion. Does light obey Newton's laws? So, but everything else obeys Newton's laws, right? So, study of light is going to dominate the historical background for both relativity and quantum mechanics. Comes because of light, always light, stupid light. Eventually, we'll figure out through our study of those to figure out how to deal with light and how to understand it, right? So it's not like it's no longer really an open question. We understand it pretty well now. But it is the driving force behind the discoveries of the early 20th century, which is what this class is mostly about. When we say modern physics, we don't mean recent physics. We mean, as opposed to classical physics. Modern physics starts in 1900 roughly. A little bit before that, though, I need to give you a background. Anyone take an E and M here? Right? All right. That's fine. I was just curious. I'm going to tell you about a few laws. One is called Faraday's law. When you take E and M, you'll do this in mathematical detail. Let me give you the English quick version of it, which is a changing magnetic field. That's like a magnet, right? A changing magnetic field also changes the electric field. That is to say, you take a magnet. When it's just sitting there, it's fine. But if you move it, the magnetic field at any point will change because the distance from the magnet will change. So if you take a loop of wire connected to a voltmeter, which measures, or an ammeter measures the current in the wire, it will read out 0 because it's just a wire, there's nothing in it, right? There's no battery or something, right? So it'll just read out 0. But if you take a magnet and move it through the wire, then when the magnet is moving, you will get a current in the wire. That's the electric field. Okay? So when the magnetic field changes, the electric field changes. Cool. That's what Faraday discovered. Very, very interesting discovery. You'll learn about it more in ENM.
But it does have to be a change in magnetic field?
It has to be changing. So when the magnet stops in the middle, the current will go down to 0. It has to be a moving magnetic field. Okay? This is, by the way, basically how a generator works. You figure out a way to turn a magnet. You figure out a way to move a magnet using something else. The moving magnet will cause a current to flow in something, and then you send that current down to the power lines. That's what a generator is. You'll build one in E&M, I believe. Okay, the other interesting law is called Maxwell-Ampere law. There's actually a lot to the end. Most of the physics class is spent focusing on the Ampere part of this law, but Maxwell added a small term to the end that is usually negligible, but it made the following important statement, which I'm going to focus on, which is that a changing electric field changes the magnetic field. Okay, so I totally remember learning this in high school. So that means if you have, if you have an electronic device, you have your computer, why don't they let you use those on airplanes? Because, they tell you to turn off all electronics that you're taking off, right? Why is that? Because when you turn on your computer, what does that do? It changes the electric field. It goes from 0 to something, right? And what will that do? It will change the magnetic field. So there is no magnetic field, which means when you turn on your computer for a little bit, there will be a magnetic field. That magnetic field does not stay in your computer. It goes everywhere. And by Faraday's law, that change in magnetic field can then interfere with the electronics of other things, including the plane, which is not what you want.
So you're telling me that if I
don't know what I
want to apply, it could destroy the electronic
Say it again?
Not destroy it, just disrupt it.
Destroy it.
Yeah,
It
it
changes.
changes it.
Changes.
It'll mess with their readings.
Yeah, so it messes with stuff and they want to be safe. They want to make sure you're not interfering. They call it electromagnetic interference, and it's actually a big deal with electronics. Okay, so here's the problem. So when I first learned this, I was like, wait, anyone see my issue with this? Even?
Yeah, well, wouldn't it just keep going and spiral out of control?
Right, and then and then change the magnetic field, change the electric field, change the magnetic field, change the electric field, change that, and right? So,
I really hope I got
the
that.
problem is I said changes. I didn't say it makes it bigger. It could make it smaller as well.
It's not 100% conversion, is it?
It is.
It is 100% conversion?
Yeah, it's efficient. It's not 100% conversion, but there's no energy lost. There's no heat or anything. It's an efficient. So it does in fact, but it doesn't blow up. It can change in different directions. So these are actually mathematical laws, they're differential equations. Dr. Hawker on the first day of class writes them up there and then derives the solution for you. I think he's crazy because that's fairly advanced multivariable calculus. And I'm not going to do that to you. I'm going to tell you the answer. Also, I don't remember how to do derivation anymore. So I'm just going to tell you the answer. So Maxwell, it used to just be Ampere's law. Maxwell added on a little term under this assumption based off some experiments he had done. Okay? And so they added this term, so they call it the Maxwell-Ampere law. So it's like, okay, so what exactly happens when you change an electric field? What's going to happen? Well, then the magnetic field changes, the electric field changes, the magnetic, so what's going to actually happen? So you can solve this mathematically. And Maxwell did that. It's actually not even that hard, I just don't remember right. I can't do it right now, and anyway, most of you don't know vector calculus, so I don't think it would be that helpful at the moment.
Let's go.
And if you do know vector calculus, I can look up the solution sometime later or something. If this is the electric field, right? This is this. He finds out that what happens is you solve the equation, and you get something that looks like this.
Wait.
Never seen that before.
Yeah, right? You get a wave, a sine or cosine wave, sinusoidal behavior. And for the magnetic field, you also get a wave. So it doesn't make it blow up out of control. It creates a wave. Now, I've drawn it like steady state. Really, the wave moves, right? Because when it stops changing, then it stops emitting this thing, and then you just have this wave shooting out this way. Okay? So here is the cool part.
Oh boy.
Maxwell takes this law, and he takes these laws, and he puts them together and solves them for wave. The wave equation is well understood at this point. It's a general description of waves, and he discovers that you combine these to create a wave equation. And when you do that, the wave equation also tells you the velocity of the wave, how fast the wave is moving. If you take a sound of light, you done that already, right? So you do the velocity of the wave, but using these calculations. So you find the velocity of the wave, and you find the velocity of the wave is this. Okay, what's that? Well, if you haven't taken E&M, I guess these aren't familiar terms, symbols. This is called the permittivity of free space, but it's basically how strong the electric force is. Okay, I mean it's a scale, a proportionality factor that tells you how strong the electric force is. Kind of similar to Newton's constant G, big capital G. Remember that? That tells you how strong gravitational force is. This tells you how strong electric force is. This is roughly speaking. Okay, I mean you'll learn taking and you'll learn this in more detail. And this guy tells you how strong, I guess. Good, how strong the magnetic force is. So this is called permittivity of free space. They call it permeability of free space. This stuff is intro stuff. You don't need to worry about this very much. We're just setting the stage for you. This is all E&M. You'll cover it in E&M. But the cool thing is this. This is the important part. These quantities were already known. This one was measured by Coulomb, like 200 years before. This one was measured by Ampere. Ampere's law, Ampere, right? So those constants were already known. He did not need to do a single experiment. The numbers were already there. All he did was combine the existing laws to figure out that it forms a wave. And then when he takes the wave, by the way, since this is a wave of electricity and magnetism, what are you supposed to be called a wave?
Electromagnetic.
Yeah, you call it electromagnetic. Get it? So this says you get an electromagnetic wave. Right? Okay, now here's the cool part. He just takes the existing numbers, plugs them into here without doing a single experiment, and he gets a remarkable answer. He gets 3 times 10 to the 8th meters per second, which is fast. But 3 times 10 to the 8th meters per second is another number that's already been measured. It is the speed of light. That's also been measured already. So all these numbers have been measured already. Maxwell didn't need to do an experiment. What he did was he showed theoretically how 3 different laws, which were assumed to be in, or 3 different sort of fields, right? Electricity, magnetism, and light, are actually all connected together. They're all manifestations of the same thing. Okay? Given that electromagnetic waves come out to travel at the speed of light, there's a very sensible conclusion you can make about light, which is
It's a wave.
light is an electromagnetic wave. So we say
I'm killed.
light is an electromagnetic wave. It is hard to overstate how cool this is. This is a major, major breakthrough. Probably the most important, most significant physics breakthrough between Newton and Einstein is Maxwell's equations. They're called Maxwell's equations. There's 4 of them, and together they explain all of electricity, all of magnetism, and all of light and optics. They're all explained by the 4 Maxwell equations. And they're incredibly successful. They still stand to this day as an extremely powerful theory. It was awesome. So once he showed this connection, everyone's like, "Oh my gosh, Maxwell, you're a genius." And he's like, "I know." And then we're like, "All right." And everyone's like, "This is so cool." Actually, at this point, they said, because they figured out quite a few other things by this point, this was when they started advising kids not to go into physics, because you would be out of a job. You were just about to finish up to figure it out. All of it. Okay? Because Maxwell had finished up the last of the stuff that Newton had not taken care of, basically. Right? Newton had not done too much with electricity and magnetism and optics. He only done a little bit. They fleshed it out a bit, but Maxwell pulled it all together and made basically the Newton's laws of electromagnetism. Combine that with the actual Newton's laws, gravity plus the laws of motion, and you got more or less everything. Everything else is just a few little details to pick up. So they're like, yeah, we're just about done with physics. However, after a little bit of reflection, we realized there was an issue with Maxwell's equations, and the issue has to do with reference frames. Because this is a velocity, right? This is a velocity. What does that mean? It's a velocity. It needs to. I need to what? I need to find a reference frame. So in which reference frame does light move at 3 times 10 to the 8 meters per second? So right, that's a real question.
That's a good question.
Because you say that's the speed of light, and of course we can't move that fast, so we don't see any. You can't measure any distance, especially not turn of the century, the turn of the beginning of the 20th century, which is when this happened, you can't measure any difference by moving or anything like that. Yeah, not yet. Although they do come with a clever one, I'll explain in a moment. So you have this idea, and you're like, okay, that's the speed of light, then which reference frame? Okay, the solution that came up to this originally was brilliant and wrong. I want to go over it so that you understand that brilliant solutions can still be wrong. Okay? It's actually a really clever one. So, by the way, this is wrong. Okay? I just want to make sure that's in your notes. I don't want anyone writing this on the test. Okay? But they came up with this brilliant wrong solution. That is, there is a preferred reference frame, a special one.
Didn't you tell us that's not true?
What do you say?
Did you say that there is no specific reference frame?
I know, so this is a change, right? That's why it's so clever. You have to break the old ideas, okay? There's certain reference. Here's one more problem. Light is a wave. People who study waves would all know that waves always have to travel through a medium, right? So light is a wave, or light travels through a medium. What's the medium of light? Don't say air, it goes through space, the sun and all that, right?
Photon.
The photon is not a medium.
Well, yeah, but that's how light works.
And they didn't know about it back then. And anyway, you still haven't answered the question because you just give me a word. A vacuum, that's not a thing. That's the opposite of a thing. So people were trying to figure out what is the medium of light. Actual equations work so well, it must be a wave. But what is its medium? Well, this one came up with the idea. Space is filled with an invisible, intangible fluid called, fluid is anything, air is a fluid too,
yeah.
Not solid is a fluid, called, great name, luminiferous ether. Okay.
Why'd they call it that?
Because it's luminiferous. It carries light. It's the medium.
No, I get the luminiferous part. Why the ether?
Ether because you can't see it. That's what ether means.
Yeah.
Seriously, you can't
I didn't
touch
know
it.
that.
Okay. Before you scoff at the idea of an invisible, intangible fluid, let me do what's there. Have you ever seen a radio wave? Have you ever felt one? How do you know they're there? Okay, so it's not that actually that big deal. You believe in all sorts of invisible, intangible things. Okay. And really, when was the last time you saw an electron? You know. So, not to mention like a orbital shell or a DNA molecule, or you don't see enzymes, you can't see them. So anyway, moving on. So this is their assumption. It's actually really clever because you see the preferred reference frame is the reference frame of the ether. The rest frame of the ether is where light is at this speed, and space is filled with it, and the light travels through it. So it solves both problems. You solve the medium of light, here it is, and it solves the reference frame problem. Very clever solution. Nothing wrong with it intrinsically, except for the fact that it is wrong. You know what I mean? Like at the time, it was a perfectly good theory. However, two physicists named Nicholson and Morley did a brilliant, very well done experiment. Because here's the thing: if this is the sun, this is the Earth, it goes around the sun. Then whatever the reference frame of the ether is, the Earth must be moving relative to it because it's going in a circle. And we're assuming the ether is not moving around in a circle, right? Because that's not how reference frames generally work. So we assume that therefore the Earth must have some velocity relative to the ether. So that means if the Earth has some velocity relative to the ether, that means it's moving through. That means we're moving relative to the ether. That means light should go at a slightly different speed this way as it does this way. Because the Earth is moving one way, not the other way. Right? So therefore you should measure small differences in the velocity of light. So Nicholson and Morley did this using a very clever interferometry device that's actually extremely sensitive. They measured the difference in the distance in the speeds of light as you changed direction. Put two things at right angles and then put them on in a thinner oil, I think, or maybe it was something liquid like that, and then turn it very slowly to see how the difference between these changed as you move like that. They discovered there's no difference between them, and it never changed. So that's not. They actually hung this for quite a while, trying to work out other arguments called ether drag, that the Earth goes through and it like pulls the ether along with it, but that had other problems because that should make the Earth slow down, and that would be bad. And so eventually, though, we were unable to make it work. Okay, now we jump ahead to a German man who had done poorly in school,
Oh, there we go.
but not because he was dumb, and he did not flunk math.
He did
not
not
flunk.
accomplish.
I wonder
But he didn't like school. He didn't like doing their practice problems. He didn't like doing their stuff. He liked doing his own stuff. In fact, he apparently copied physics homework off of his roommate, so he could go spend his time doing his own stuff. Okay? Because he didn't like school, school didn't like him either. So when he finished school, he was unable to get a job in academics because he couldn't get any recommendations because no one liked him, and he didn't like them very much either. So because of that, he could not get a job in academia, and so he went, but he had to find some way to support his wife and child. And so I believe by then his child was no longer illegitimate. I believe he married her by that point. And so he got a job. Later on, he divorced her to marry his cousin. So yeah, great at physics doesn't mean you're great at everything. So he got a job as a patent clerk, reviewing patent applications. You know, you check that. That's actually not a simple job. It's not saying it's a post office clerk, which I always thought it was. You're not like snapping things. You actually have to think quite a bit about it. People are putting in patents. You have to decide, do we already have one of these that fit the legal requirements? It requires training. It requires science. So it's not like a nothing job, okay? But it's not what he wanted to do because it's not physics research.
Of course he did.
This was in the year 1905, on the side, while maintaining a full-time job as a patent clerk and helping raise his family. Although it was 1905, so he probably didn't help very much, let's be honest. This gentleman publishes 4 papers on the side. By the way, that's already nuts. I get one paper every like 5 years. He publishes 4 papers that year. Each paper by itself is a Nobel Prize's worth of physics. He only won the Nobel Prize for one of them, but he could have won it for any of them. And the one we're going to talk about, it's actually a pair of papers. The 2 we're going to talk about. One of them is on Brownian motion, which establishes the atomic theory of matter and kicks off creates the field of statistical mechanics. And one of them is on the photoelectric effect, which we'll talk about later, and it establishes the field of quantum mechanics by itself. That's the one he won the Nobel Prize for. We won't even have time to talk about Brownian motion, we don't have time. And then the other 2 are about Maxwell's equations and reference frames. And those 2 papers are worth like several Nobel Prizes. Because the man we're talking about is, of course, Albert Einstein. And the reputation he gets is well deserved. He discovered a lot, and he did most of it in 1 year, part-time, without being paid. Without experiments. He took only existing experiments and explained existing experimental results theoretically. He had no experiments of his own in that year because he was busy. So, but they were brilliant explanations that have all turned out since to be true, which helps. And so he took the entire physics world by storm, and by the way, got a physics job after that. So let's talk about what he said. Einstein reportedly had dreams about this. Weird dreams about trying to chase light. He said, Nicholson and Morley showed light goes the same direction no matter what you do. The same speed no matter which way you're turning. The ether argument is not working, but the Earth is moving, we know that, right? So how can there be no change in the speed of light? The Earth is definitely moving. Look, I'm standing on a train, this is me. I throw the ball at, give me speed.
5 miles an hour.
5 miles an hour. I'm not very strong. So I put the ball 5 miles an hour. However, the train is moving at
20 miles an hour.
20 miles an hour.
Slow.
Okay.
It's not so slow.
Trains can be that slow. That's a slow road.
That's a life like
This is you watching me. When you see the ball, how fast is the ball going? 25 miles an hour. It's boosted by the train, right? Okay. The Earth is moving. And if you're measuring differences, we know the Earth is only moving in one direction at a time, right? So if you're measuring differences, you should see this effect with everything on the Earth, right? You have to measure very sensitively, but they did that. You should see a difference with different directions. Why isn't light speed changing? That's what Einstein was trying to figure out. Apparently had weird dreams, supposedly had a weird dream about chasing a particle of light, or chasing a light beam. and not being able to catch up. And he comes up with the weirdest, probably the weirdest, strangest idea anyone has ever proposed. There's probably a few other ones that has turned out to be right. And he comes up with what we now call special theory of relativity. You will not be impressed by it at first.
But I will.
It says, laws of physics are the same in every inertial reference frame. What's inertial mean again? Constant velocity. Okay. Laws of physics are the same in every inertial reference frame. Yeah.
It's underwhelming.
Kind of intentional on my part. I consider it German. Okay. This might seem familiar to you. What does it kind of seem like? Sounds like that Galilean one we did last time, right? I mean, it's pretty similar, right? but all that's really changed is we discovered a few new laws of physics. In particular, if anything is the laws of physics, it's got to be what? Yeah, Maxwell's equations. Maxwell's equations work so incredibly well, they're definitely laws of physics. Okay? So, the laws of physics must include Maxwell's equations. But Maxwell's equations by themselves, without anything else, Maxwell's equations by themselves predict what? They predict what?
Speed of light.
Speed of light. Okay? You can get the speed of light from Maxwell's equations. If Maxwell's equations are a law of physics, then that means the speed of light is a law of physics.
Which means it's the same for inertial.
Okay? Other speeds are not like that. Other speeds are not derived. The speed of a baseball is not derived. You just depends on how hard you throw it, right? But the speed of light is fixed by Maxwell's equations. Therefore, Maxwell's equations are laws of physics. The speed of light is a law of physics.
Which means it's the same.
Whoa! That means, therefore, the speed of light is the same in every inertial reference frame. And that is all of special relativity. That's the entirety of it. That's the whole theory. The speed of light will stay the same in every inertial reference frame.
You're right, that doesn't seem very impressive.
Okay, why is that a problem? Well, let's look at this example again.
Oh, we did that. Okay.
Now you have me here, but instead of a ball, I have a flashlight. And it shoots something that goes at speed c. C is the speed of light. 3 times 10 to the 8 we always use c for it from Latin. Hilarious, something like that. Okay, now you're standing here and the train is moving. Let's say the train is moving a lot faster than 20 miles an hour. Let's say the train is moving at half the speed of light. Okay. Now, according to you then, how fast is that light being going when you're watching me?
Speed of light.
You would expect it to be 1.5 c, but instead, according to Einstein, it's still c. Now, how can you two agree on that? One of you is definitely moving faster. And not only that, let's say you're standing here and light is moving away from you. You measure how fast it's moving away from you is going at c, right? Okay. Then because I'm very fast, I run after that speed of that light particle at 0.99 c, 99% the speed of light. It's quite fast, but I won't count. That's a lie, by the way. I run after it, right? So you see me going very fast, and the light particle going very fast, but I'm going almost as fast.
Yeah.
What do I see the light particle doing? It's going away from me just as fast as you see it going away from me. Making it impossible to catch up light. I don't mean you can't catch it, you can't even get close to it. When you run faster, it goes away from you just the same speed. See, the stuff of nightmares. So what does that mean? Well, I give you a little bit of homework, easier I think than tonight's, inviting you to think about it. Don't look online.
I can see why you got that dream.
Don't look up. Yeah, you don't want to get the dream. Don't look online. Okay, you don't need it. I'm not creative, guys. Creative enterprise, right? So don't look online. Think about it. Talk to people about it. Figure out. But some of the problems are very straightforward. A lot of them aren't that. Okay, but there's some problems at the end I want you to think about carefully and see what you can come up with. Okay. All right.
So I'm going to create a shared document.
Oh, okay, yeah.
Micah, wait. Everybody at this table, wait, actually.
My due dates are so Monday, Tuesday, Friday.
There you go, my dude.
Write down your Gmail so that I can make a shared notes folder.
Can I just mention that that's really cool because hold on a second, yeah. Even if you're moving at 0.99C, the light is still relative to you moving at C, not at 0.01C. That's fun.
It's a nightmare.
It is. Because you can never even get anywhere close to it. You could move it like 0.999.